Okay, so here is another approach to teaching the nature of science, and that's through the use of analogies. So distinguishing between, for example, a metaphor and analogy, they're both bridges from one thing that is not understood to something that um, the students are already familiar with. So in that way, they're bridges. The difference between the two, metaphor and analogy, is a metaphor likens two things but doesn't map them out, doesn't say how they're similar, how they're different. In analogies, we always try to do that so that we're not creating misconceptions with students. Okay, with that said, just to review, what aspects of the nature of science can we reasonably expect to teach? We're going to focus on one aspect that we can teach using an analogy, and that's the functions and relationships of theory and law. So first of all, we ask the question, what is a scientific law? And we pose the students with, after the activity, perhaps, what's a scientific theory? Now, one approach is to use this model. This is a black box activity, for those of you familiar with that, where you can't look into the mechanisms or what is inside of the box, or in this case, a tube. And students are expected to make inferences. In this case, they're pulling strings in this demonstration model. This is a pretty big model, and it allows students to consider why we use models, and one of them is scale. This tube that could be used, I'll demonstrate during the workshop, allows students to imagine what is inside that would make the ropes behave the way that they do. Then you might give, after the students come up with a number of rules, hint, hint, laws, they're going to end up coming up with a theory. Of course, both of those, law and the theory, likened to what they're constructing, is going to be after the activity, during a reflection. However, this tube represents a paper tube, like a toilet paper tube or a roll of paper tube, and students take a piece of string, and they take that string and construct it. They are given a bunch of different materials that they could possibly come up with the same mechanisms, the same rules demonstrated as they did with the larger model, the model that I gave them. They're constructing their own model, and that might be that when you pull the left upper rope, that the right lower rope goes in. That would be an example of a law. Anyway, so from this, students, we liken the relationships that they see with the tubes to the relationships of physical phenomena. And then the model that they create, we liken to a scientific theory, inferred explanations for observable phenomena. Of course, these definitions, these are really at a I would say probably a high school level. You're going to perhaps adapt those for 8th grade, let's say, but you wouldn't be introducing, of course, distinguishing between laws and theories during the elementary grades, likely. However, this tube is great for just observation and inference. You don't have to be teaching about laws and theories to your elementary students. You can work on other powers of the mind. One thing you can also do with this is to send students to the library, and this is one where they'll never come back, because you ask for one instance in which a theory has become a law. There are two different types of knowledge, and this is important in the case where we say, where some might say, well, the theory of evolution is just a theory, it hasn't become a law yet. That will never happen. Laws don't become theories, and in fact, theories don't necessarily precede laws. Biology, for example, Mendel's laws, gene theory, Mendel's laws came first and then the explanation came later. Same with physics, Newton's laws and special relativity. Chemistry, Boyle's law, Charles's law, ideal gas law. Those are kind of misaligned here, but the idea being that the laws came before the actual explanation, the kinetic molecular theory.